Hello, in this video we will cover lines and planes. All right, so we're going to start off by discussing lines, and in particular we're going to start with the vector form of a line. So the vector form of a line, this is a way to introduce what the final form of the line that is used in a multivariable calculus course, and it's primarily a theory-based introduction. So I just want to be clear about that the initial definition that I'm going to give you is not going to be the final definition, and that we're going to transition at some point to the final definition that will actually be useful for going through and doing problems. So this is a little bit theory based. It gets into the idea behind the actual definition for the practical equation of a line. Okay, so we're going to start off with this. So this is the vector form of a line, and it has some components here, right? So it has what's called R naught, okay? And so you can think of R naught as it's an initial vector that terminates on the line. And then we're going to have vector v. This is called the direction. This is defined as the direction vector. And it gives the direction of the line. And finally, we have two more, t. So t is the, if you think of the direction vector as the direction that the line heads in, t is enables us to go through and use multiples of v to define the entire line. So oops, negative infinity. And then finally, r itself is just a general vector that terminates on the line. So it acts a bit like x and y in previous line equations, right? Like y equals mx plus b. You have x and y are generic, and you have m and b are set, and x and y is any point that's going to be on the line. R is kind of our general catch-all for things that are going to end up being on the line, like x and y before. All right, so let me show you a picture so you can kind of wrap your head around the theory behind this definition. Okay, so suppose we have an xy axis. So we're going to start off with r naught, this initial vector, and it starts at the origin, and it terminates on our line. So we're going to say that point there, where at the end of the point is a point that happens to be on our line, and then so that's r naught, and then after that we're going to go through and add v to that, and v is going to be the direction that the line heads in from there. So you could have the line be this way or this way or this way. I'm going to do it this way so that we kind of get the maximum amount of offset. Okay, so that's v. And then the way in which that we go through and that defines the line is that t here, because t varies from negative infinity to infinity, you end up taking multiples of v, both positive and negative. And if you took positive multiples, like if this is v, then 2v would be here, 3v would be here. And so you can end up defining the line in the positive direction by doing positive t values in this, they go this way, and then we could have negative t values that go the opposite way. And so you could end up with, let's see if I can get this right. That's pretty good. We end up with that line there. And then the way that R works here is that you start off with R naught and then you add these multiples of V. And what do you end up getting if you do that? Well, if you recall our addition definition for vectors, then R naught plus V would be this vector here. All right. And if we had 2v, we would end up getting this vector, maybe not quite that far. We would end up getting this vector here. If we had v twice, right? So if we took r naught and added v twice, we would end up here. And then the sum of those, r naught plus 2v, would generate this r vector here. If you did a negative v, right? If you did -1 for t, then you'd end up getting negative v, right? Would take us this way. And so we would end up getting this vector would end up being r. And so what r is it's just a general vector that ends up terminating on the line that corresponds to lots of different t values that you end up plugging in. And so you can end up going through and generating the line by actually setting specific t values. So this t value here, this point here would be when t is 1, right? Because we did r plus 1v. This point here would be when t is 2, because we did r plus v twice, right? 2 v's. This point here would end up corresponding to -1 for t. And so we would have t equals -1. And so you'd end up getting that r value. And so if you do t from negative infinity to infinity, you end up getting the entire line ends up being generated. And so that forms the basis for our vector form of a line. Is its vectors are all of which terminate on the line that are created by starting with an r naught that gets us out to the line and then adding or subtracting multiples of v to go through and generate the positive and the negative direction for the line. Okay, so that is the vector form, and that's the basic explanation for how it works. Okay, so why have a vector form of a line? Aren't our current definitions doing a great job of defining lines? Yes, they are in 2 dimensions. However, the nice thing about the vector form of a line is that I drew all of this in 2 dimensions, but all of it could be extended to 3 dimensions and nothing would have to change. Okay, so if you go through and draw a 3-dimensional coordinate axis, oops. If we went through and picked a point somewhere in here and said, okay, well, that point's going to be our starting point, you could have r naught go out to it. Okay, so let's just pick a spot and say here. Okay, we'll say that's r naught. Okay, and to go through and give us some dimensionality to it, we could just drop this down and say, there's our r naught. It's directly above this point here. And then from there, we could go through and have our direction vector v. And one more other thing. So r naught in this case, of course, would have 3 components, not 2 components. So that's what differentiates 2 dimensions from 3 dimensions. And then we could still have a direction vector that, of course, also has 3 components. And I don't know, we'll just pick a direction here. How about this way? We'll say that's our v. And so if you go through and take R naught and add V, let me move our R naught here. It's kind of in the way. It's going to end up being in the way when we go the negative direction. But if you go through and take R naught and add V, you'll end up getting that vector there, which would be R. And then you could add another V, right, which would take the line further out. And you could end up getting another vector that terminates there. And you could take vector V in the negative direction. And you could get an R that terminates there. And so you could still go through and use the exact same method to end up defining this line here. Oh, that was better the first time. That where R naught moves out to that line, and then V gives us the direction for that line, which enables us to go through and generate the values. And so the method that we just used for 2 dimensions can be very simply extended to 3 dimensions. And that's the point of the vector form of a line, is that it has more utility than our mx plus b form does, which is limited to just 2 dimensions. Okay, so as I started off by saying, all of this is all kind of the theory behind the definition, the theory behind how we could go through and define a line instead of using a point and a slope like we do in 2 dimensions. Instead, we've extended it, and essentially we're using a point and a direction vector, a vector. So a vector has more utility than a slope does. But it's still kind of a theory based. You know, we would like something that easy to use, where we could go through and just plug things into, and it would end up generating lines. And so that's what we're going to do next. Let's go ahead and take our vector form of a line and try and translate it into something more useful. So how do we do that? Well, what we can do, so let's just start off by writing our form. So it's R equals R naught plus T times V. Is we can go through and we can say, let R equal a generic X, comma, Y. Let R naught equal a specific point, a vector that terminates at a specific point, Y naught, X naught, Y naught. And then let's just let V equal A, comma, B. All right. And then if we take those things and just plug them in, what happens? So we're going to get X, comma, Y equal X naught, comma, Y naught plus T times A, comma, B. And then this is just a scalar multiple of the vector, so we can bring it in by multiplying it by both of the components. And then when you add vectors, you add the components. And then when 2 vectors are equal, they have the same components. So and this can be translated into X equals X naught plus AT, y equals y naught plus bt. And this form, this equation here is called the parametric form of a line. And the way it works is that if you want to go through and define the equation of a line and you have a point that the line passes through, and you have a direction that the line heads in, a direction vector, then if you put the two together and put the point here and the direction vector here, then you'll end up with the parametric form of the line. And it's that simple. It's just like y equals mx plus b. Just plug the point and the direction vector in, and you end up getting the equation for the line. Let's do an example. So let's find the equation of the line that passes through one, 3 with direction vector 2, -1. So you don't have to go through and do this, but let's just sketch the picture just to kind of make the connections. Okay, so if we were to draw this, so we've got 1, 3. And then we have, so that if we were to go through and put an R naught on here, then this would be R naught. It would go from the origin and it would stop right here on that point. And then we've got direction 2, 1. Okay, so starting here, 2, 1, we would go 2 to the right and down 1. Let's say that's about 2 units. And so if that's our direction vector, then multiples of it will enable us to go through and define the line. Okay, and so that's basically what the information we've got here. So 1, 3, you could think of this here as being our R naught. Now, again, you don't have to do all this stuff. I'm just kind of showing it to you to try and make the connection between the this example and the previous stuff that we've covered. So this R naught and then V and then multiples of V define the line. Okay, as far as just going through and using this, it's actually really quite simple. If we have x equals x naught plus at and y equals y naught plus bt, then to go through and find the equation, we're just going to plug in the appropriate information. Now, the one thing is you've got to make sure to put the information in the right spot. So the point goes here, right? So the point goes in this place where the x naught and the y naught are. So we'll have 1 and 3. And then the vector part here goes here next to the t. So we're going to have plus 2t and then minus t. And that's the answer right there. All right, so x equals 1 plus 2t, y equals 3 minus t. Okay, so one skill that you do want to be able to develop is to look at this and be able to pull that information out, pull out this information. And so you do want to be able to look at this and say, okay, well, if I'm given this parametric equation, then the line goes through the point 1, 3, right there. And then the direction vector is going to be 2, -1. So I'm going to go 2 to the right and down 1 from 1, 3, 2 to the right and then down 1. And so you do want to be able to go both ways. So starting off with this information and plugging it in to generate the equation, or starting with the equation and being able to pull out this information. Okay, so there's an example. Let's do a second example. So let's find the equation of the line passing through -1, 2, and 1, 3. Okay, so if we're going to go through and find the equation of a line, one of the things that you're going to have to get used to is making sure that you have enough information. So it's very similar to going back to 2 dimensions and y equals mx plus b, right? Whenever you go to try and find the equation of a line using slope-intercept form, you know that you need a slope and you need a y-intercept. If you don't have either the slope or the y-intercept, then you don't have enough information to go through and define the line. So you need to go through and find that information from what you're given. Okay, so the same thing is going to be true when it comes to going through and defining lines using vectors. So we need to have a point and a direction vector. Now, if you're given a problem such as this, where we are not given the direction vector, then what that means is that you have to go find it. So how could we find the direction vector given 2 points? Well, the way that you could do that is you could go through and you could find the vector between the 2 points. Okay, and to do that, if you recall from the vector video, we go through and we subtract the components. So you're going to do 1 minus -1 and 3 minus 2. And we get 1 minus -1 is 2. 3 minus 2 is 1. So the direction vector for the line that passes through these 2 points is going to be 2, 1. And without actually going through, and another thing that you can do is you can actually create a sketch without actually drawing a coordinate axis and all that. So we could say if this is -1, 2, and this is 1, 3, and what we want is we want the line that passes through them, then it makes sense that the direction vector, the direction of the direction vector would be the vector that goes between the 2 points. And to find that vector, you would do 1, 3 minus -1, 2 in vector form. Okay, so once we have this vector, then all of the heavy lifting has been done, and we can just go right to our solution. X equals x naught plus at, y equals y naught plus bt. And so just take that and plug in the information we have. So as far as the point, you can use either point, and you'll still end up getting the right answer. If you start off with this point, then there's some nice things will happen. So let's just do that, and I can show them to you. So we're going to get -1, and then y equals 2. And then as far as the vector, then we're going to have plus 2t and plus t. Okay, so what nice things happen if you use this point for your initial point, and when you define your vector, if you did this point minus this point, well, the nice thing is that if you take t equals 0 and plug it in, you get x equals -1 and y equals 2. And then if you do t equals 1, you'll get x equals, well, -1 plus 2 is going to be 1, and then 2 plus 1 would be 3. And so what we've ended up doing is we've defined the line such that when t is 0 and t is 1, you've got the directionality goes such that it goes from this point through that point in that order. Now, there's a variety of different things you could do in here that would make it so that that would not be the case, where if you plugged in t equals 0 and t equals 1, you didn't get the 2 points in that order. So I want to be clear that it's because of the way in which we structured this. That doesn't always happen. And if you do have a line that's different, an equation that's different from this, but still ends up following this same format, you still get the right answer. It's just the way that we did it nicely sets up this way. And so later on in the course, we'll end up encountering a situation where we want to create line segments. And the way in which I went through and did this problem is the way in which you can go through and define a line segment, where when t equals 0, you're at one point, and when t equals 1, you're at the other point. And so it's just kind of this piece here. If you go through and restrict your definition from t, you'll end up getting a line that just goes from this point to this point. So I'll explain one more time what I did to do that in case you do encounter a situation where you want to create a line segment. So it gave me the 2 points. I defined some directionality to my direction vector by doing the second point minus the first point. If you think of this as A and this is B, then vector A, B, you subtract vector B from vector A. And then once you've got your direction vector, then you're going to want to use A for your point. So if you use A for your point and AB for your vector, then you'll end up with this situation. Okay, and then let's do one more example. So just so you can illustrate that this works in 3 dimensions. Okay, so let's say we have a similar problem, but we've got -1, 2, 4, and 5, -3, 2. So the first thing that we want to do is again, you can draw a picture for it if you want. You don't have to, but you can. We got -1, 2, 4. Let's say that's there, and we've got 5, -3, 2. We'll say that's there, and we want to go through and find the equation of the line that passes through those 2 points. So to do that, anytime we're trying to go through and find the equation of a line, we know that we need a point and we need a direction vector. So they did not give us a direction vector, so we need to create one. And to create one, you can use the points and just subtract them. Subtract the coordinates. All right, so we've got 5 minus -1, that's going to be 6. -3 minus 2, that's going to be -5. And 2 minus 4, that's -2. And so once you've got your direction vector, you can go through and just plug into the formula. Now the formula, if you're going to go through and use 3 dimensions, then you need to add a third component, a third equation, I guess in this case. And so we're going to get z0 plus ct, okay, is the way that you write the third equation in your parametric form. And from there, you just take the information, pick one of the points, plug it in, put your vector, plug it in, and it's done. All right, so we could, again, use this point so that we've got the appropriate directionality. So it's going from this point through that point. And what are we going to get? We're going to get -1 for x0, then plus 6t, and then y equals 2 minus 5t, and then z equals 4 plus minus 2t. And there we go. We've got our equation of our line that passes through -1, 2, 4, and with direction vector 6, -5, -2. Okay, so the next thing we're going to look at, so that's our definition of our line, our vector form, and then our parametric form that ends up being kind of our practical form that we end up using mainly throughout the rest of the course. Next thing we want to do is we want to do something similar for planes. Okay. So our definition is that. Okay. And so we're going to go through and very similar. Let's just define these. So R naught, again, you could think of it as an initial point on the plane. We could think of R as a general point that's on the plane. Again, similar to y equals mx plus b. It's just the y and the x. It's any old point that ends up being on the line. Oh, whoops, I should say these are vectors. Initial vector that terminates on the plane. And then we've got a general vector that terminates on the plane. And then finally we have n. So n is a vector that is orthogonal to the plane. So the n it stands for normal, and so sometimes you'll hear the term normal, and it will be used interchangeably with orthogonal. So this is called the normal vector. So we don't call it the orthogonal vector, we call it the normal vector. Okay, and then picture-wise, what do we have happening here? So, again, we could start off with three-dimensional coordinate axis. Let's say that we have a plane. Okay, so this represents the plane. Of course, this extends in every direction infinitely. I'm just drawing, a portion of the plane. Okay, and let's go ahead and put some stuff on here. So we'll say that point is where R naught terminates. And we'll say this point is where R terminates. Okay, so that's R, and that's R naught. And then if you go through and subtract them, what ends up happening? Well, think about that. All right, if you subtract R and R naught, so again, we recall the way subtraction works for vectors. When we subtract two vectors, you get the vector that points from the end of one point to the end of the other, or from the end of one vector to the end of the other. And so what is going to be true about this vector, no matter where R is, right? So R naught is fixed, it's here, but we could move R around on this, and no matter where we end up putting R, what is going to end up being true about this vector that's R minus R naught? Okay, well, what is going to be true is that R minus R naught is going to end up being a vector on the plane. Again, no matter where we put R, no matter how we move it around, this vector here, that's on the right-hand side here, it's going to move around too with that, but it's always going to end up being on this plane, on this, if you think of a piece of paper, on the piece of paper. Okay, and so that's important to understand that that's what R minus R naught is this is a vector on the plane. Okay, and then finally we have N, which let's just throw it over here. Okay, now that is a vector that, what is it? It's orthogonal to the plane, so it's at a 90-degree angle. And it's just sitting here off to the side here. Okay, and now what happens if you take a vector that's on the plane and you dot it with a vector that's orthogonal to the plane, right? This is orthogonal. Then you end up getting 0. All right, so we've got a vector on the plane dotted with a vector orthogonal to the plane. And so that's the basis for the vector form of a plane. That's the idea behind it, is that you have a general vector that's somewhere on, that terminates somewhere on the plane. You've got a specific vector that terminates at a specific given point that's on the plane. When you subtract those two, it creates a vector that's on the plane. And if you dot that with the normal vector, then you end up always getting 0. Okay. All right. Now, again, that's kind of the theory, the basic idea behind the vector form of a plane. In order to transition, we want to translate this. We want to translate it from the vector form of a plane to what I'm going to call the general form of a plane. How do we do that? It's very similar to what we did when we did the translation for lines. We want to go through and define R naught. We'll say that that's going to be X naught, Y naught, Z naught. Let's define R. That's going to be X, Y, Z. And let's define N, and we'll call it A, B, C. And then if we have R minus R naught dotted with N equals 0, now it's just a matter of plugging all that in. So here we're going to put X, Y, Z. Oops. Minus X naught, Y naught, Z naught. Let's give us R minus R naught dotted with A, B, C. Okay, now in order to go through any of the simplifying, first we want to do the subtraction here. When we subtract vectors, we subtract component-wise. So we're going to get X minus X naught, Y minus Y naught, Z minus Z naught, dotted with A, B, C. And then when you do the dot product here, the dot product, we do component-wise multiplication, and we add. So we're going to get A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught equals 0. Okay, and that is going to be our general form for a plane. We're going to use that throughout the semester. Pretty much whenever we want to go through and define a plane, this is the format we will use. The thing that you need to plug into this to define it is you need a point, which is X naught, comma Y naught, comma Z naught, and you need a normal vector, a vector orthogonal to the plane. A, C. Okay, assuming you have point and normal vector, you pop them in here, just like the good old days in y equals mx plus b, and then you're done, and you have your equation. Okay, nothing more needs to be done except for just to take these two things and pop them in, assuming that you've got them. Now, one more thing I do want to show you that you sometimes see is you sometimes kind of see this alternate form. And the way that it looks is it's ax plus by plus cz equals d. I'm just going to put this as the alternate form. And what's been done to generate this alternate form, if you want to think of this as a starting point, is they went through and they took A and distributed it, B and distributed it, C and distributed it, and then they moved this AX naught, BY naught, and CZ naught. They combined them and moved them over to the other side. So you could think of it like that has happened. Okay. Now, if you're given this alternate form, what information can you derive from it? You cannot just at a glance derive a point, but you can derive a normal vector. So the normal vector in this alternate form is still A, B, C. It's the things that are multiplied by X, Y, and Z. And if you want to pull a point out of this, the way that you can create a point is you can set two of the variables to 0 and then solve for the third. It's probably the easiest way to do it. So for example, you could take x equals 0, y equals 0, and then just divide d by c, and you'll have the point 0, 0, d over c, and that will be a point that lies on the plane. Okay, so that we've got our general equation for a plane. We talked about the information that you need and the alternate form that sometimes you see. So let's go through and do an example. All right. Find the equation of the plane. Containing -1, 3, -2 with normal vector (1, 4, -3). Okay, again, you don't need to go through and draw a picture for these, but it's not a bad idea to be capable of doing so. And so when it comes to drawing a picture of a plane, you'll notice the easiest way to do it is to not use a coordinate axis, because the coordinate axis kind of makes it difficult to position the plane. The easiest way to do it is just to draw, just kind of off in space here and say, hey, this is my plane. And then I can go through and I can just generically define these things. So -1, 3, -2. I'm just going to say, let's let that point be -1, 3, -2. And let's go through and just say that this vector, we're told it's the normal vector. So we'll just draw a vector on our picture and say that vector n equals 1, 4, -3. And that gives us a representation for the information that we were given here. Now, again, totally unnecessary, but it's a good practice. As far as going through and defining the equation, all we need to do once we've got a point and the normal vector is to just take those and plug them in. So here's our general form. And so A, B, C are going to be our components from our normal vector, and X naught, Y naught, Z naught are point values. So we're going to have 1 times x minus -1. Well, it's going to be plus 1. And then b is going to be 4. And we'll get y minus 3. And then z is going to be -3. And we'll have z minus -2. That's going to be z plus 2 equals 0. And that's it. And you're done. Okay. So there's an equation. There's an example of how to go through and find the equation of a plane given a point and a normal vector. You just take them and plug them in. All right, so let's do one more example. Let's say we're asked to go through and find the equation of the plane containing one for -6 that is orthogonal to the line x equals 3 minus t, y equals -1 plus 2t, z equals 2 minus 3t. Okay, so this time they gave us a point that's on the plane, and they told us a line that is orthogonal to the plane. Okay, so when we go through and find the equation of a plane, it's important to know the information that you need. Again, harkening back to y equals mx plus b, you can't define a line, slope-intercept form of a line, without a y-intercept and a slope. You can't define the equation of a plane without a point and a normal vector. So if we are not given a point and a normal vector, then you have to go through and find that information. And so if you look at this problem, we're given the point, but we're not given the normal vector. So how could we go through and find the normal vector? Well, one thing that you can do, you could go through and you could draw a picture. Maybe not strictly necessary, but again, it's good practice. So we can go through and say, hey, this is our point, 1, 4, -6. And then what is this? It's a line that is orthogonal. So let's draw a line that's passing through our plane like that. Okay, and we know that that line is orthogonal to the plane. And what do we got from that line? Well, we have a point. Now, it's important to understand the point that they gave here. We don't know that that point is on our plane. So you want to just put that somewhere off in space. Just assume it's not on the plane. It's most likely it's not. And so we'll have 3, -1, 2 is over here off to the side. And then we have a direction vector that defines the direction for the line. V equals -1 to -3. Okay. And so now we've got all the information and it's on our picture. We've got our point. We've got our line, point and direction vector. And now the question is, can we go through and find the information that we need for the plane? Well, the information we need a point, check. We need a normal vector. Do we have a normal vector? Well, if you look at this line, the direction vector for the line, right, looks an awful lot like a normal vector, right? It's going to point in the direction that is orthogonal to the plane. And so we could use the direction vector as the normal vector for the plane. So we could just go through and say n equals v, which equals -1 to -3. And then from there, it's just a matter of going through and plugging in the point and the normal vector into the plane equation, right? So we have a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And then just take the normal vector and the point and plug them in. So a is going to be -1, x minus 1, b is going to be 2, y minus 4, c is going to be -3, z minus -6, which is going to be z plus 6, equals 0. And there we go. We have our answer. Okay, so those are the basics for defining lines and planes. So I'm going to create a second video that has more difficult problems involving lines and planes, where we've got to go through and use some of the information we've learned in previous sections, such as the cross product, to go through and define lines and planes. We can mix lines and planes together, so you could have a plane, you could have two planes and be asked to find the line of intersection of the two. You could have a line that lies on a plane and then be asked to go through and use that information to find, and some other information to find the equation of that plane. So there's a number of different ways we can take lines and planes and previous information and combine them all to make very complicated, challenging problems. And so I'm going to go over some of those problems in a separate video. But thank you for watching this video, and I'll see you next time.